Okay, so the Bellman-Ford algorithm just takes the recursive formula we derived on the shortest path and implement it in a very straightforward way. So we start this table, the first row of the table we initialize to 0, right? So every vertex has an entry, and the rows are the generation or the iteration. And of course we set the distance from source to itself to 0. And now we have k, which is the number of hops, right? And for every vertex we just set the new distance to be the old distance, right? And then we try to update it, right? For every edge that comes into V, we take the minimum of the current distance that is there together with the distance to U with k minus hop plus the price of the UV edge, right? And we update dvk to be the minimum of this, and we do it over all the edges. So clearly this is going to take off m time, right? Because really, it's true that we are doing a loop on the vertices here, but if you really think about it, this is really a loop on the edges, right? We go over all the edges and we do this update, right? This update, by the way, we will encounter it later on, is sometimes referred to as relaxing the edge, UV. So this is going to take off m time, and we are doing it n minus 1 times, so the running time of this block would be mn, right? And we are just following the recursive formula from before. There is nothing else. And then we just update the distances to be the distances stored in dvn minus 1, right? So this is just a simple implementation of this recursive formula that we derived, where to remind you again, dvk is just the minimum length path from S to V using k or less steps. Right? That's all it is. Okay. Okay, so the running time we already discussed. As far as the space, well, one have to be careful, right? So we need to, this table dvk, the vertices, there are n choices, the generation, there are n choices. So together, this is going to be n squared, right? And formally, usually, a graph representation don't have the incoming edges, right? So because of that, we need to compute it, right? We need to compute for every vertex all the incoming edges into it. So storing those reverse adjacency lists, this is going to take off m space. So overall, the space is of mn squared. But in fact, one can reduce the space to mn, because observe that in every point in time, we just need the previous value, k minus 1 and k, right? So in this table that we are filling, we need to remember only 2 rows. So this is of n, but there's also a way to see it using other approaches, which we will see next. Okay, so this is a more direct way of doing it, where we now have only a single array. Instead of having this, we don't keep the value of dvk for every generation. Instead, we just fill it with the array, and then we go over the edges and we do this relax operation, right? D of v is the minimum of dv du plus the edge before it, right? So so it's easy, well, easy is not the right word, but if there is no negative cycles, one can verify that this algorithm, in fact, is equivalent to the previous algorithm. Notice that this is not completely obvious, because it's now quite possible that dv would contain shorter paths that have more edges, but the intuition is that we don't mind getting ahead of ourselves. That's kind of the intuition. But, you know, for the time being, let's not worry about it. Figuring out why this is correct, in fact, would follow quite easily from a later algorithm we will see. Okay. And the space clearly now is m plus n, right? Because we have only one array. The O of m, we still have to pay for those reverse adjacency list. Okay, so this is it.